Hello, welcome everyone to this session about protecting equipment health with IoT in power and utilities. My name is Silvia Prieto and I'm an IoT specialist based out of London. With me today is Madhuri Perry, Senior Manager for AI ML based out in California. Let me please introduce you to the agenda for today. We will start with a bit of an introduction to who this presentation is for. We will talk a little bit about power and utilities trends, what predictive maintenance is, what business outcomes we can achieve by using this technology. And then we will dive a little bit deeper into the current state, constraints, and future options. Then we will get a bit more technical and we will talk about some architecture options and finally finishing with a demo at the end. So who is this session for? We want to have this presentation for business leaders because we want to provide insights on what benefits of using this technology we have. Then IT leaders and subject matter experts so that we can show them what options we have within the AI and ML technologies. And then lastly, with OT leaders so that we can explain the benefits of using these technologies into their day-to-day operations. So let's start with some business metrics. One business metric that we can improve by 20% is process uptime. This is due to operations, maintenance improvements, and audit mitigations. The second one is capital utilization. This is improved because we are able to perform and manage the assets with more efficiency and extend the operational life. Third, we have operational expenses that we can reduce by up to 30%. Why is this? Because we can reduce the breakdowns, we can eliminate also unplanned maintenance, and by obviously increases in performance. And then lastly, all these elements, they translate as well as a reduction in carbon footprint of 3 to 4%, which will help companies achieve the sustainability goals. So let's talk now about some industry challenges that we see from AWS in these industries. First, we see the aging networks need to comply with regulatory bodies' metrics. And this is obviously a challenge because these aging networks have been in place sometimes in the water industry, for example, for more than 100 years. Then is also the challenge of always trying to reduce costs, trying to keep down the operations and maintenance curve. Third, is trying to maintain the uptime and reliability of the networks so the utilities can serve the customers best and avoid any kind of liability for lack of service. Then we see, for example, in the utility, electricity utility, the new ways of working. For example, when these networks were designed 50, 70 years ago sometimes, they were designed so that the power station will distribute energy into the grid and that energy will then reach people's homes. Now we see not just an exponential growth on energy usage, but the use of EVs and also the extra electronic devices that everybody has in their homes today, but also the generation of electricity by solar panels and wind turbines, which basically has transformed a one-way network into a two-way network. Then we also have the climate change's impacts, which are starting to get worse year by year, and also trying to help companies into achieving the sustainability goals. But let's put this challenge into numbers so we can see the picture of what's really happening. In the electricity utilities, we see 100 billion costs per year on the US economy because of these outages, of which almost a third is because of equipment failure, which can be really reduced and mitigated by this new technology of machine learning. And why are these assets failing? Well, because most of them are 10 years plus above their lifespan. On the graphic on the right, you can see the two lines, which is how much will be the cost if nothing changes, if we keep operating these assets the same way they've been operating over the past few years. And if there was a huge improvement in investment into improving these assets, then the last two lines at the bottom will see, which is still way above to where we are today. So something needs to be done if we really want to reduce these risks. The aging asset is also a very big problem for the water industry. You can see on the right-hand side of the graph that the cost is also increasing in a very similar way than the utilities one for the electricity. For example, and to put this into context, there are 300,000 water leaks breaks every year in the US alone, which equals to one every 2 minutes. This translates to 2.1 trillion gallons of water wasted every year, of which equal to 7.6 billion loss. This loss needs to be noted that it's not just the cost of fixing this issue, but it's also the energy that was used to clean and treat that water before it was wasted. So it's the complete cost of all those leaks. And what are the challenges that these companies are facing when they are trying to optimize those assets based on these problems that they are facing? So we basically see three. First is the lack of visibility on the asset performance. So there's lack of monitoring. Some of these assets have, as I said, very, very old, more than 50 years, some of them, more than 100 years in the water segment, and they don't have any kind of connectivity or intelligence. Some of them might have it, the more recent ones, but most of the information is built into silos, which is very difficult to extract, analyze, and process. Then we have the problem that most of these utilities are in the firefighting mode versus in strategic improvement, which means that they're spending most of the time trying to fix issues, which is very costly because they don't have the time to try to plan this maintenance in advance to try to minimize costs. And then we are seeing that most of the knowledge workers that they are closing to retirement, and the information on how to maintain these assets is going away with them. Unless we are able to make the infrastructure and the analytics having those insights as well, this information is potentially going to be lost. So I've mentioned a few times now what predictive maintenance, about predictive maintenance. So please now let me explain exactly what I mean when I say this. Traditionally, there has been, as we consider phase one in the left graph, which is when we try to fix the assets by only fixing them when they break. So we do nothing, very low initial cost, and then we just fix them whenever they breaks. The problem with this is that we might be liable to penalties or insurance claims if something goes wrong because we are stopping a customer's supply or service. Then we evolve and then we start thinking, okay, let's try to do maintenance every few months, every few years, every few weeks, or every few hours, depending on the asset. In that way, we can do maintenance before things break. And then lastly, we have the new wave, which is the predictive and prescriptive maintenance, which is the one that we are talking about and focusing today. So why is this better? Well, let me explain you first how it works. So you will take the data, you will train the model, and you will get anomaly detection. That anomaly detection will basically be able to help you diagnose. Diagnose what? The root cause of that anomaly. So once you know the root cause, what you can do is start with the prediction of when will be the best time to change what and when. In that way, you will have the best tools to minimize the cost to make those changes. And why is this the case that this one is cheaper? Well, if we look on the right-hand side, you'll see the total cost and the preventive cost and the reactive cost. So the reactive cost, as I mentioned before, is very low at the beginning because it doesn't cost you anything. And then it starts to go up as the time goes by because you will get more and more errors and faults and outages. Preventive fixed cost, if you start very, very at the beginning, so if you do it very often before things started to break, then it gets really expensive. But then as the number of errors are meant to happen, then that preventative cost basically deletes any errors that can happen, so it becomes cheaper. So what we're trying to do with predictive maintenance is to find that sweet spot in the middle, which is the preventive maintenance interval that you can see, the purple line, and that is the minimum cost of both lines together. And that's what we want to achieve with machine learning. Now, let's talk about some of the numbers that come with each of them. So for reactive maintenance, so when we fix only when it fails, we know that at the beginning it's obviously very cheap because it doesn't cost much, but then, as I mentioned, you have liabilities, you have penalties, and you have other costs that will add to the bill because of lack of service. Then when companies move to preventive maintenance, they saw a reduction of 8 to 12%, which is significant, but it's not as much as it could be. And the reason is because people think that some of the assets go through a very deterministic line when things will fail. And the reality is that even though it says things will fail every X amount of hours, sometimes they fail before that for many different reasons. 82% in reality is actually random issues and patterns that will not be able to be detected otherwise. So when we move to the predictive and prescriptive maintenance, that is when we really see these big cost reductions, up to 30% for cost, 30 to 40% on downtime, and 75% on breakdowns reduction, which is really, really significant cost. Still, based on this data, we still see that most utilities still work on the first two boxes, reactive failure and preventive maintenance. And today, now I will show a couple of examples of customers who are moving though to their box on the right, to the most using machine learning intelligence. So first, I have Woodside. Woodside is an Australian company, gas natural manufacturer and producer. And what they have done is created a plant in Australia as well that has more than 200,000 IoT sensors connected to the cloud. They're able to perform thousands of analyses and more than 3 million daily calculations with the aim to see exactly what's going on the plant and to use this information to do preventive maintenance. Not only that, because of these changes and move to the cloud, they were able to change the culture in the company from a utility that was changing improvements that will take sometimes over years to months and weeks. And that is basically creating a new culture of innovation within the company where they want to push the boundaries and make a difference. Then electricity utility in Italy, Enel, we've done with them an important project in Italy where they wanted to control and monitor 15 minutes energy intervals for their customers. That was a legal requirement that was given by them, by the government, and they had to comply with. So they've sent to their cabins 500,000 cabinets across Italy with a gateway, each gateway with more than 100 smart meters. With this information and with this project, what they also did is to add extra intelligence. They have seismic sensors, they have temperature sensor as well, and they're also able to monitor the equipment that is within that cabin to try to also do predictive maintenance on them. And then lastly, Innovyze. Innovyze is one of our partners based out in the US, but with global reach. And basically what they have developed using AWS services is a platform that can bring in real time analytics and operations information. Why are they able to achieve this platform? Well, savings on operating expenses of up to 20%, water loss reduction of 20%, and overall increasing efficiency and reducing risk. And with this, I hand over to my colleague Madhuri. Thank you so much for your attention.
Thank you, Sylvia, for the introduction and setting the case for predictive maintenance. What you're going to see here in the second part of the presentation is really going over what are the technical elements of it and how companies like yourself have put together the various components of the data from the equipment and how the ML portion of it comes to enable the insights for folks that are operating, maintaining, and performing predictive maintenance for these equipments in the field. As part of this solution, the opening context that I want to set here is really giving you a picture of art of the possible. As you can see on the screen here, there are 4 fundamental components to this. The first one, of course, everything starts with the assets that you have. And that primarily goes into whether the data from the asset, the telemetry from the asset is available, in which systems are they available. And from there, you are looking to go in, either supplement it through some other sources of data that you have from the maintenance or the historical data of the assets and so on and so forth. Sometimes it's not always sensor data, it's also vision related data, whether it is in the form of a manufacturing line. Typically, we see customers having that form of a defects, or if you're supplementing some of the analog systems in equipment that is decades old, that could be a component as well. Regardless of the data source, you are trying to get information about the current performance of the asset. And that's the current state of the asset. And that information you're plugging into the second section here, and that's where the intelligence part comes in. So you have anomaly detection, diagnostics, and based on those insights, coming up with the mitigation strategy for your assets. All of these are part of the prescriptive recommendations that you expect the predictive maintenance solution to provide to you. And all of these insights, they are fed into your third component, which is the command center. And either it's through visualization by leveraging some of the existing tools, or it could be in some of the digital transformation company initiatives, things like simulations, like what if I were to reduce the engine speed by 10 RPM, is that going to last longer? All of those simulations feed into the insights of the command center as well. Once you know the current state of the assets as part of visualization, and then you have your simulation insights, you're going to take actions here, and that's where your orchestration comes in. If your say for example, one of the asset, you see that the predictive maintenance is indicating that it's going to fail in say 2 months time frame, how are you going to tie that into this fourth component of, should I order a replacement part now or maybe 30 days from now? If I order now, will I get any early financial discount that would help with the procurement of it? All of those conditions into analysis go into your command center decision process as well. So the fourth element here, that's where all of your existing on the ground processes and your other work stream related insights on how long is it going to track this particular shipment from a given vendor. Would this particular vendor A have a higher failure rate of components, or is it the vendor B? So all of these decisions go into your mitigation techniques on how you're going to choose the insights that you receive from these assets. So that's the full life cycle, so to speak, of what we are trying to achieve. We are going to start addressing one by one as we go through the presentation. So the first slide here, as we take this journey for the remainder of this presentation, I want to first focus on data gathering aspect. So this data, it could be gathered from your industrial systems, the PLCs, the SCADAs. You might also have historians like OSI Pi or Kepware or something else that is already on your floor of the industrial system that you have. And this is basically where you would hop off into an upstream journey to get to that central data backbone that you would build for your operations and industrial architecture. So based on the PLC data, SCADA data, sometimes it's sensor data, whether it is any of the existing sensors you have, or you might choose to add any net new sensors, still the data from there, all of those would have to feed upstream. On top of all of this, how you are aggregating all of this data through your existing OT network architecture to send it upstream to AWS cloud is what is seen into the right of the screen here. What you're seeing there is really AWS Greengrass service. That's the one that is going to have the various adapters to obtain the data from your existing systems. So this is just the very first step of data gathering. So if we were to just break it down a little further, in as part of a demo that I'm going to show you later, we are going to use a sample information of a time series data from France, fans. And this sample data is a really good capture of how existing compressors or even fans, turbines, all of these work in the power and utilities space. So this particular equipment, primarily you will notice on the floor that they will have various initial wares that they started out with. They will have manufacturing variations. They'll have various operating conditions as well. And these operational settings could affect the performance as well. The data that I'm going to use has been contaminated with some sensor noise just to keep it as close to the real life scenario as you encounter. In addition, I also have used varying conditions of the sensor data along with some of the fault modes that the equipment could generate. So what you're seeing here primarily is a sample data set. I know it's a lot of numbers, but what you're seeing here in the first column is really a bunch of engines, and those have different operating conditions and set of sensor data. We'll explore this data later on as part of the demo as well. So you might be wondering, what do I do with this data? So this data is coming from most of the equipment that's in the floor. So from here to create that upstream journey and the path to the cloud, you need a set of hardware, and this hardware will be your aggregation point for all the data within the shop floor. The second layer on top of the hardware is your software, which is really having all of those pre-built runtime libraries that will help you ingest the messages, do some pre-processing action on those data and the telemetry, and from there also have the adapters, which is the application code based on what historian do you have on the shop floor, so on and so forth. All of these three various components are required as step one to be able to get that data liberated from the factory floor and upstream into the cloud. So from here, I just want to touch upon one of the core components that we are going to highlight here, which is the software layer with AWS IoT Greengrass. The Greengrass provides local actions for remote control, the machine learning inference, and from there extracting the data and moving ahead. From there, what you're really seeing is the actual data processing at the edge on Greengrass. So all the time series data we accumulated from this equipment is going to be pre-processed by Greengrass. And from there, you could add serverless compute we call as Lambda. It's a bunch of code that you have the ability to execute at the edge on your shop floor. That will basically transform your data and prep it to get to the next state upstream into the cloud. So as we put together this architecture, what you're seeing is you already saw the step one where we collected the data from all these equipment. Then the step two is where the data is going to get processed. So this is where we are going to ingest the data in the cloud from all of these equipment and systems. And that primarily goes through the IoT device gateway in this particular case. And you have some form of a rule defined. Say, for example, if engine is rotating between temperatures X and Y, that's regular operations as normal. However, if it breaches the threshold of Y, go ahead and notify somebody. So that's the IoT rule that you're going to apply on top of the data. Likewise, pretty sure each of your equipment will have its own rule sets that go with it on the need for raising alarms or what are the low thresholds, high thresholds, and so on. So based on the data velocity, as we call it, how fast the data is coming or how slow it is coming, you have various data sources, AWS services that fit the bill. If the data is a high velocity data, you have Amazon Kinesis that will help you process that data without having any scalability issues. If it is a key value pair, you'll use Amazon Dynamo database, and so on and so forth. I haven't really put every single service out there. There are a lot of options available. But the end of it all, what you're really looking at is placing this data in the appropriate data store based on how you're going to use and retrieve the data. For the context of this presentation, we are going to have the data in Amazon S3. That's our hop off point for the intelligence that we bring to the table through SageMaker algorithms and so on for predictive maintenance. So what we are going to do now is, given that we have collected the data, we have performed some form of pre-processing, we're going to go ahead and get the ML machine learning aspect of it addressed now. So as part of the machine learning intelligence, a typical workflow comprises of all these steps that you are seeing here. It evaluates a variety of models to identify the best model for your use case of the data that you have done. As you can see, the traditional development process is pretty complex, it's expensive, it's iterative. So what we have as part of AWS done is introduced a service called Lookout for Equipment, and that primarily abstracts away the white box that you see on the screen here. It is taking away the complexity that is involved in identifying the right algorithm, taking the data and performing the hypertuning, so on and so forth, into a more simplified fashion. So what you're seeing is, with Amazon Lookout for Equipment, you feed in the data, it's going to do all of the heavy lifting for you and primarily provide you the output or evaluation of how the data is going to be used to create the insights you need for predictive maintenance. So primarily what we are seeing is, the takeaway from this slide is, you are improving the workflow tremendously through an automated service to reduce the resource utilization. And not only that, you are also increasing the speed of execution from months to hours. So as you think back to your own sites and the shop floor, what I would encourage you to think is looking at the data that you already have available and primarily using it readily to gain some insights through some of the managed services we have here. So that's the component, putting it back in the architecture layout for you. That's the third step, where we have leveraged either a custom model through a SageMaker, which is a managed service for all the data science needs, or we could use the Amazon Lookout for Equipment, one of the choices, regardless of where you are in your journey, to be able to derive those machine learning insights to gain that predictive maintenance capabilities. And from now, what we are going to see here is a little bit under the hood visibility for the IT audience in you. So what you're really looking at is, when you're having this data come in and you are having your SageMaker service perform some insights, what you would get is that data is coming in from S3, where we have landed all of the data prior and kept it ready to go for SageMaker to consume. Now you might ask, hey, wait a second, my asset is really not working 24/7 all the time, sending data, but it has operational windows. Maybe during the shift change, it has like a slowdown time, like a half an hour or what have you, and then put it back on. So in that case, what that really translates to at a data layer is, the time series data that's coming from the equipment will come in batches. So to accommodate that behavior of an asset, what we have is a feature called batch transform. So that basically uses the newer insights or the data that comes in to generate additional insights based on the latest version. So that's what you're seeing here. And basically you have a Lambda function, which is basically going to create a transformation job, leverage the batch transform function, and generate the insights for the customers. That primarily means that at the end of the machine learning inference process, you will have a set of numbers that are available for you to consume. What does that really mean? So each of these numbers would have to be consumed by your downstream applications, whether it is inside being, if the rule breaches, send me a notification. That's an Amazon SNS. If the data comes in and there is an analyst or a operations lead looking at daily charts or reports. That dashboards can be presented through Amazon QuickSight. That's yet another way to go about it. Or you might say, hey, you know what, once you get the insights, just leave it where it is available within the Amazon ecosystem as part of ML Insights, persisted to some form of a data source, and I will pull it through into my third-party custom ISV where I consume all of the insights. That would be the API gateway channel. So just to pull this all together, I just put together a demo here that I want to showcase to you. Here is a training data set. Each row is a snapshot of data taken during a single operational cycle, and each column is a different variable. The columns correspond to the unit number of the engine, the time in cycles, and there are 3 operational settings for each of these engines that we are using in the dataset. And the remainder are the sensor measurements in the columns here through the end of it. So just to walk through one of the examples here, for example, if you take row 4 here, that's representing engine ID 3, time in cycles as 26, there are 3 operational settings, and the data from all of the sensors is represented here. Now let's see the machine learning Jupyter notebook here. You have the standard libraries that are getting imported. And what we are going to do is, as I mentioned before, the NASA turbofan dataset that you have seen earlier is going to be used in this notebook. And the training data is just getting read here as using certain Panda libraries. And just for visual comprehension, I have gone ahead and used the plots from the various sensor data. As you can see, there are a lot of sensor data, and over a period of time here, you can see different data points captured in the graph. Now, what we are going to see here is a set of training data that has been uploaded for S3 for a bunch of processing work. I would just skip over this to focus on the main items here. So now here what we are seeing is a machine learning model that is being invoked, and that's primarily taking a set of hyperparameters on how many GPUs I want to use, what's the batch size of the data, so on and so forth, and eventually launching a training job. This training job is going to crunch through the data that we have created, which is already available in the S3 bucket. Now, if you were to go back and consider a real engine that is running, it would have various operating states, some up and down times, and so on and so forth. So as the data comes into the S3 bucket as batches, you would need to have the intelligence built in that takes the batches of the data and processes that to make more near real-time inferences as the data comes in. So that functionality is accomplished through your machine learning SageMaker batch transform feature, and that would enable you to get the predictions on the data set as it comes around. So this is the set of Python code that is making that happen. You are eventually performing latest inferences on the batch data and posting the model prediction results back to the S3 bucket. So once you have the data that has been crunched through by your model and posted back into your S3 bucket, I find it better to visualize it through a bunch of plots that will help us understand what that data really means. So what I have done here is, as you can see, set
a plot up with the remaining useful life of the engine, which is our predictive maintenance goal here in this session. And that remaining useful life is seen on the x-axis. And what you're seeing here is on the y-axis, the engine ID. So you can see from these graphs that average RUL, remaining useful life of the engine, is around 200 to 250, and some operate in a better, some engines operate at a higher efficiency, some go, of course the operating life is falling down as the engine is getting older and older. That brings us to the end of the demo. So once you have the data, I mentioned to you that one of the ways you could consume the data is through QuickSight. QuickSight is one of the services from Amazon. It's a dashboarding service for you, and that primarily will help you visualize and do a lot of insightful things with your data. I have just plotted it like the way I said, with the remaining useful life on the x-axis and the engine ID on the y-axis. As you can see with various colors, those are all the remaining useful life as part of different runs that have happened in the past. As new batches of data comes in, it's going to keep adjusting or provide the latest iterations remaining useful life. These are depending on how frequently you want to look at it, or how maybe on a daily basis, monthly basis, that would be the insight that your command center will be knowledgeable to take. The next slide here, what you're seeing is putting it all together in the form of a technical architecture, and that primarily gives you the actions you could take, whether it is in the form of adjusting your machine setting, that is the IoT shadow, that's how you adjust your equipment's operational settings, or it could be deploying a new model, which is basically gather some additional insights before you take that action. All of those are communicated back to the equipment, and that's how you basically integrate your action that you have taken to the equipment itself. In addition, the actions could be something that you would integrate with your maintenance logs are updated, your scheduling, or you create a work order for somebody to go perform predictive maintenance, or it could be just scheduling resources availabilities with the equipment scheduled downtime that you think will be most viable for your environment. All of these put together is providing you the predictive maintenance solution. As you can see, it's fundamentally going through 4 steps. To summarize it all, you need to unlock the data that is in the equipment. The second thing is you process the data. The third thing is you derive those insights. And the fourth thing is really you take the action, and that makes the most sense for your predictive maintenance solution. Thank you for being here.